Hello and welcome to the 26th lecture in this series. And last time I was still in the process of describing various examples, important examples which arise from the regular value theorem. So the last thing I had started on was the graph of a smooth function. Well, the setup was I had an open set U in Rn and a smooth function f on U. Graph is the set of points x f of x in Rn plus 1. Now I'd like to describe this as the level set of a function which is defined on U cross R. Notice that U cross R is an open subset of Rn plus 1. So on this open subset I put this function phi of xs is equal to f of x minus s. Then phi inverse 0 is the graph of f. Now, so let us now put it in the framework of the regular value theorem and prove that this is indeed a submanifold of Rn plus 1. So for that, all I need to do is check that the derivative of this, which is again a map, just as in the previous case of SL and R, this derivative is now a map from Rn plus 1 to R. So I just have to check that it's a non-zero map. So I have to find one vector where it's non-zero. So let's see what the derivative actually looks like. Let P belong to phi inverse 0 equal to S. Let P belong to phi inverse 0 equal to S. So I just have to check d phi at P from Rn plus 1 to R. I have to look at the rank of this linear transformation, and since the target is one dimensional, it's enough to show, if I can find a single vector in Rn plus 1 whose image is non-zero, then I'll note that this map is surjective. So in fact, let's just take this d phi P of the vector 0, 1. So the first n coordinates are 0 and the last coordinate is 1. Now this, in order to calculate this, I'll take a curve passing through the point P in the direction 0, 1, compose it with phi and calculate the derivative. So this is d by dt of phi of P plus t times 0, 1 evaluated at t equals 0. And that is the same as d by dt of phi of, so here now let me take this point P in S has two coordinates. One, let's call it alpha, f of alpha. Then P plus t times 0, 1 will be alpha comma f of alpha plus t. At t equal to 0, and that is the same as going by the definition of phi. It's just the second coordinate minus f of the first coordinate, f of alpha plus t minus f of alpha at t equals 0. So I'm just left with t, derivative of t, which is 1. So we immediately see that 0 is a regular value of this map phi, of this function phi, and the graph is a level set of this corresponding to this regular value. So therefore it's a submanifold. Therefore the graph is a submanifold. Now, if one is just interested in checking that the graph is actually a manifold, there's a more direct way of doing it. One can also see that a graph is a manifold of dimension n as follows. So, in fact, the graph is just diffeomorphic to the open set U that we started with. So, I'll define a map, the projection map from the graph S to U in a very simple way, which is so the graph consists of points of the form x comma f of x, and I just project it to U x itself. So now pi is actually a homeomorphism. In other words, pi is obviously continuous and pi is bijective as well. It's clearly one-to-one and it's clearly surjective as well. And pi inverse, the inverse map is also easy to describe. From U to S is just pi inverse of x. I'll just put it at height f of x. That's it. Right. So pi is actually, so pi is a homeomorphism, and therefore pi provides a single chart. So there's a S is covered by single chart, and the topology on S is coming from Rn plus 1. With that topology, this S itself, so S is covered by single chart, and that's given by pi. So one can put a smooth manifold structure on S in a very trivial way via a single chart. And it's a small exercise to check that the single chart structure and the smooth structure given by the regular value theorem are the same. Right. So now I would like to say a few words. In many of the examples, for example, the case of the graph or the special linear group SLNR, it turned out that the submanifold that we get is one dimension less than the ambient dimension of the ambient manifold. In that case, we say that the submanifold is a hypersurface. If Mn contained in n plus 1 is a submanifold, we say that M is a hypersurface M is a hypersurface of N. Now I would like to describe, so yeah, right. So now that I had this, going back to the case of the graph, given a smooth function, I was able to get a hypersurface in Rn plus 1. Here's a converse to that proposition. Let M be a hypersurface of Rn plus 1. Then locally is locally M is the graph of a smooth function. And we already seen that the graph of a smooth function can be realized as the level set of some other function. It's a level set of another function. So the proof is quite simple. So when I say locally M is the graph of a smooth function, what I mean is that given a point P in M, I'd like to find an open set around P, and that portion of that. So for instance, actually the case of the sphere is good enough. When I have a sphere, I know that locally I can, so for instance, graph of a smooth function. Well, I know that every point on the sphere lies in if I am in the upper hemisphere, then this is in the graph of the certain function. Similarly, if I am in the lower hemisphere, I am in the graph of a certain function, and that description continues to hold even when this I'm on the equator. So for instance, so as an example, let's look at the case of S2 inside R3. If I'm in the upper closure of the upper hemisphere, so that including points on the equator, then any point can be written as x comma x is in R2 and square root of 1 minus x squared. So this function square root of 1 minus x squared will serve is the function for which the graph is what we have here. Now, so the one wants a similar statement here. So take it. So let's start with let P belong to M, let P belong, and let U phi be a chart for chart around P. So here actually what I need is not just a chart, I need a slice chart. Be a slice chart around P. So then M intersection U now a slice chart by definition has the property that the portion of U which intersects with M is taken to, in the case of a hypersurface, phi will take M intersection U to Rn. So in other words, the last coordinate becomes 0. So it's a set of all x in U such that phi n plus 1 x equal to 0, because phi is actually a diffeomorphism, which so the picture is that this is P. I have a bigger open set, and this portion is taken to something in Rn. So this is the n plus first coordinate, xn plus 1. And so this is phi. So phi inverse of, if I look at where phi n plus 1 becomes 0, that precisely corresponds to M intersection U. All right. Now this immediately tells us that, also note that d phi n plus 1, if I look at this d phi n plus 1 at the point P, is not equal to 0, not the 0 map. So here I am thinking of phi n plus 1 as a map from U to R. And then the claim is that this derivative is not 0. So this can, to see that this is not 0, since d phi n plus 1 acting on V is, so let me write it slightly different way. So this is actually, yeah, the point is that phi takes U in M intersection U to Rn. So the point is that because of this property, if I take any vector V which is not in the tangent space to, so this will imply here d phi, the tangent space to S is actually equal to Rn itself. Phi is a diffeomorphism, and this is contained in Rn plus 1. So the tangent space to S is taken to this special subspace Rn by under phi. So that means that if I take a vector V, since V not in the tangent space to S, then d phi plus 1, the last coordinate, cannot be 0. If it had been 0, then remember that d phi is supposed to be an isomorphism. Then it would, from this equation, if this part had been 0, then it would mean that d phi of V would actually be inside this Rn by definition of the last coordinate. So, but that would mean that V would actually have to come from TPS. So which is not the case since I took V not in. So this is not 0. So in short, what I have is that here I've already shown that this is actually M intersection U can be realized as the level set. Once I have a, so now I have a level set, right. So actually, so what I've shown is that this, if I start with a hypersurface, I have, I can write it locally as a level set, hence a hypersurface is locally a level set corresponding to a regular value of some smooth function, and that smooth function just came from the looking at the last coordinate of a slice chart. Well, one can pursue this further, then and then one would like to write it as actually the graph of a, and that part is also clear how to write it as a graph. Again, to see that this is M intersection U, again the same portion. So I have a manifold, a hypersurface M, and I'm looking at a small portion of it, and my slice chart is pushing it down to this. So this, the slice chart is actually defined on an open set in Rn plus 1, not just an open set in M, but it takes this to this. And so to think of this the red portion, I would like to think of the red portion as a graph over the green portion. So I had already given it some names. So this, the open set, big open set, we had called U. So let's call this as let's say V. So I would like to, it's natural to try to use phi inverse to regard this as a graph, to see that M intersection U is the graph of a smooth function over V. So what we would like to do is, so phi inverse already, first phi inverse is a map from V to U. Which takes this to this green portion to the red portion. However, what I want to do is I want to want a function f from V to R such that so essentially every point of phi inverse of x should be, notice that phi inverse of x is actually a point in Rn plus 1. So maybe I would like to, I think I'll write it in, so like this, phi inverse x comma 0. So then x would be a point in, so x would have n coordinates and the n plus first coordinate is 0. So that's my v. So phi inverse of phi inverse of this point should be written as, I would like to write it as x comma f of x. So this is what I want. I want such a function. I.e. phi of x f of x equal to x comma 0, which is the same thing. Right. So now this is a sort of functional equation for f. Which functional equation for f in terms of phi. Now this is precisely the setup for another consequence of the inverse function theorem, which I didn't talk about much, which is called the implicit function theorem. So let me not go into it at this point. I'll just briefly say that the existence of f follows immediately from the implicit function theorem. Which is actually again a very quick consequence of the inverse function theorem. But since I won't be using this graphical representation all that much, I don't want to pursue this. So alright, so we'll stop here and resume with a description of tangent spaces in my next lecture. Thank you.